Okay, are we live? I think we are live. Okay, so hello people. Welcome to the Latin American Webinars in Physics. My name is Joel Jones from the PUCP in Peru, and I will be your host this day. Today, we're having a colloquium which covers topics beyond the standard webinar. Our speaker is Paula Tuzon, who will talk about particle physics and beyond. So let me tell you about her. Paula did her PhD at IFIC in Valencia, focusing on theoretical particle physics. And after completing this, she moved on as a postdoc to the IFISC at the University of Balearic Islands. There, she shifted her work to complex systems, complex networks, network dynamics, and theoretical models of diffusion. However, paella is paella, so she moved back to Valencia and got a permanent position at the University of Valencia. She's currently doing research on her previous fields, but also directs her attention to science education. This, of course, was not enough for Paula. So recently, she took a temporary leave from the university and is now working at the regional Valencian government, being the second regional minister on environmental and climate change. Right, so we have an interesting talk coming up, and we're very happy to have Paula with us. So the title of her talk is Life After Particle Physics, and we're sure she'll keep us enthralled with it. Well, before we begin, as usual, let me remind everybody that you can ask questions and comments via the YouTube live chat system, and these questions will be passed on by me to Paula at the end of her talk. So you've got the microphone, Paula. We're all yours.
Okay, thank you, Joel, and thank you everybody for being here, attending this colloquium, this seminar, and for your kind presentation. Let me share my presentation. Can you see it?
Yes, it's loaded. Yeah, perfect.
Yeah, can you see it? Okay. So this talk is called Life After Particle Physics, as Joel introduced this colloquium. And well, I am Paula Tuzon, you know already, and well, this is my contact in Twitter and other social networks. And well, I am from the University of Valencia, temporarily on leave, but this is my permanent position. So now I will tell you more details about it. The first of all is why this question is relevant. Why is relevant asking ourselves about life after particle physics? I think many of us worked in the field for many years, and some of us, after working in the field for some years, decided to switch or to change to other fields. And as I resume in the abstract very quickly, I think our education, our training as particle physics makes us versatile. So I am not going to say that it's easy, because it's never easy, but we can go to different fields, not only different from particle physics, but even for physics, and work in other jobs like applied mathematics, or to jobs where you have to build models, or where you have to do predictions, or in general try to answer things that you don't know, or programming, or whatever related with that, right? And also I think it's very characteristics of our times, because now doing physics and doing science is very different from previous last century, 20th century. I think it's very different now. Our times are very changing. The scientific careers are not so stable. Countries do not have as their priorities many times this job, and it's quite common that many of us at some point ask ourselves what to do after particle physics, or look for jobs different from particle physics or physics research after doing a long career or some years career in particle physics. Okay. So this talk is about that. Of course, the question of the colloquium is not about me, but my career maybe is an example of things that you can do in the case that you have had particle physics training, right? So different things that you can do having an education on this field. So as Joel told you at the beginning, I started doing particle physics. Now I will tell you very briefly what I did in my PhD. Then I moved to complex systems, which under a theoretical point of view, I don't think it's so different. Of course, the applied field is different, but it's very theoretical at the end, very fundamental physics at the end. And then I moved to a complete different field, which is science education, but you can use also concepts related to fundamental physics in this field, as I will tell you later. And then I did a break on politics, but this is other reasons that are not related with having a stable job or having a, it's about different reasons that came up at some point in one person's lives and so on. Okay, so this is a timeline more or less. Just sorry, I want to. Okay. This is a timeline. Just for my head, as I told you, I started here doing my PhD, then I switched in my postdoc, and my permanent position is in science education, and it is combined with politics. I mean, it's not that I switched; it's just a break. So a brief on particle physics. What did I do in my PhD? Just for you to know, very brief. I work, well, the title of my PhD thesis is Tests of the electroweak model in the presence of two Higgs doublets. I worked in phenomenology of theoretical particle physics, as many of you know this field, of course. I worked in two Higgs doublet models in general, and in my research at IFIC and in other collaborations in my stays in, I don't know, in Portugal, where I met Nico, or United States and so on, I worked in several papers that combined with this thesis. The most important is that I worked in the aligned two Higgs doublet model that provides new sources of CP violation in the Yukawa sector. So it's the standard model that is enlarged with one more Higgs doublet, and in a particular way that you can provide a general source, a new source for CP violation that we know that we need to provide. Also, this model is a general representation of all two Higgs doublet models with this particular symmetry, which is a discrete symmetry. So we kind of built a particular two Higgs doublet model that was able to describe many other ones, and also to study the parameter space in a quite easy way, to look for physics beyond the standard model. Okay. Then I also studied very deeply the charged Higgs phenomenology related to this model, and lepton flavor violation tests, flavor changing neutral currents when the mu goes to E conversion in nuclei with general operators. But these general operators can be, for example, the ones of the two Higgs doublet model. So it was related also. And finally, I did a, well, this is a collaboration with another postdoc at that time. We studied a model, a two Higgs doublet model with an extra U1 boson, a new heavy boson Z prime. That is, well, it was interesting at that time for cosmology models, although I am far from that field. So at the end, I could build, some papers, some investigation, some research about two Higgs doublet models, and I studied phenomenology. Phenomenology, you know what it means. At the end, it means that you have to calculate all the possible interactions with the new particles and the old particles, old or the standard model particles, to tell the experimental physicist where to look exactly to find the news that your model provides, right? So we were working all the time very close to the experimental point of view, and there were exciting years with my director Tony Peak. And after that, well, I knew that I wanted to switch to a more applied field. I didn't want to continue with particle physics. I prefer to do something more related to, I don't know, daily life or whatever. And someone recommended me to know this field, complex systems, and in particular a very interesting institute that it's in the Balearic Islands, that it's called IFISC, the Institute of, well, in general, complexity and this is a multidisciplinary physics institute where they study different kinds of systems. I don't know if you know complex systems, but just for you to know, I took this from the web of the institute, but because I think it's very clear. They, for example, study transport and information in quantum systems, nonlinear photonics, nonlinear dynamics in fluids, biocomplexity, and collective phenomena in social and socio-technical systems. Just to give you some examples, in quantum transportation, for example, they do studies in nanostructures, decoherence in complex systems, synchronization, quantum thermodynamics, and information processing. In fluid dynamics, for example, they study the transport of substances, how plankton, for example, find their nutrients, or transport of oxygen, or nutrients in blood, or the thermal balance that determines the climate. And they also have a group in bio things, okay, and in the biology sector, they study ecology, for example, the mobility of the organisms and their interactions to look for food, for example, how diseases propagate. This is very interesting now, for example. Spatial patterns and other interactions like competition, predation, mutualism, etc. And also in the bio group, they have a group, well, some people doing brain function studies, the neural networks that are very famous in other fields. And they have also, well, it's a field quite important also in complex systems, that is social dynamics. They study social systems and try to study them under a physical point of view to understand the dynamics. For example, how is the formation of opinions, or how is cooperation, how are cultural conflicts, the coexistence and extinction of languages. This is very interesting also. Or social learning, human mobility, transport, tourism, the new science of cities, epidemics, or energy consumption. I mean, just for you to know a little bit. There are people from different fields working together in complex systems. There are mathematicians, there are physicists, of course. There are also biologists. There are people that are programmers. I mean, it's like a multidiscipline field. And in particular, I did my postdoc in things related to social dynamics, the formation of opinions, and so on. And the tools that we used to do that, just for you to know, is computational social sciences, game theories, but statistical physics, agent-based models, complex networks theory, and big data analysis. And in particular, I use the ones that I highlight in this slide. And I worked in two very particular topics. We made a paper about models of social diffusion that reflect processes of how new products, ideas, or behaviors are adopted in a population. This is called complex contagion in networks. For example, I mean, if there's I don't know, something that is new in society and people is starting to adopt it, how this adoption process is dynamics is done in the society, right? It's like an epidemic model that I am a contagious agent and I infect another agent, and this other agent adopts this new behavior or whatever thing under a social point of view, until all the society is infected, what in this case would mean that all the society would adopt this new thing, being a mobile phone or a new computer or a new social behavior, whatever it is, right? And another topic that I focused on is we analyze the effect of competition in internet news. We analyzed a particular website where there are many news, and the news are ordered by the number of interactions the news get. So we analyzed the competition of this news, in the website. Just for you to know the study, this is just the example. I don't want to enter into many detail because this would be very long, but now because of the epidemics and the pandemics that we are having, unfortunately, we know a lot about this kind of models, this kind of epidemic models. So this model that we studied was very similar. This was an SIS model, susceptible, infective, or infectious, susceptible. Susceptible, it means you know that you are susceptible to get the illness, let's say. And infectious is, you know, you are able to infect another people. So these are the typical equations. I don't know if you are familiar with them, of an SIS model. Where rho is the density of infected people in the society, and it varies with time according to this formula, where you have the number of infected people that can interact with their neighbors, that are supposed to be distributed like this, okay? And with some probability mu, they recover, okay? If you, with some probability, would remove them, you had another term with DR, okay? So these other people would have died. But in this case, we are assuming that nobody dies in this time window. And we have susceptible infected people all the time. So what is the news of this model? The news of this model is that the probability of being infected depends on the neighborhood, depends on the structure of the neighborhood, okay? This is the new thing about the model we studied. And why is new? Because these models in general were able to predict some dynamics, but based on aggregated data, okay? However, this function comes from a paper, another paper, an investigation that comes from a phenomenological data, okay? From a phenomenon that was studied from the bottom to the top, let's say, okay? It was a study where they looked how was the behavior of different passerbys that were looking at the same point, and how this behavior propagated in the society or in the people that were passing by, okay? So we kind of did some phenomenological thing and obtained different results, okay? At the end, what you want to study is the space of parameters, the parameter space you want to determine when the dynamics becomes, I mean, where, in which point all the society becomes infected, and how is this dynamics, if you have a smooth transition or if you have a very sharp transition, and of which factors depend, and so on and so forth, okay? I don't want to go into details, but this is the parameter space. Lambda at the end is the parameter that takes account for the degree of infection, if it's very infection or not so high, and rho is the density of infected. So you have different kinds of transitions depending on the parameter, and other parameters that control the inner dynamics, and comes directly from an experiment very connected to the phenomenology. Okay, this is just an example of the many, many things that people study in complex systems. Okay, this is just for you to have a very short view of that. Well, then, as Joel told you, this is not, it was not because of paella, exactly. But, well, I was doing complex systems in Palma de Mallorca at IFISC, and it's true that it was at the same time as you remember the economical crisis of 2009, 2010, the consequences of that economical crisis, we started to see them in 2011, 2012, and so on. At least in Spain, the science field was very damaged. I think we share that in all countries, more in ones than in others, but in general it was the same. And then it was a practical decision. I mean, I knew that in the University of Valencia, in the science education department, they were going to offer a position, and they wanted, well, they wanted is something that is public, but they were looking for people with physics profile, and then I went there and I won the job, and I won the permanent position. And in science education, the good thing is that I can keep my research in previous fields, and I also can do research in science education. So it's also a multidisciplinary department, and that is very, very good for me, because I can take advantage of my previous knowledge. It's not that everything is new at that point, no? I mean, that you have to start from zero. No, it's like a continuation. You adapt to another field, and you can keep doing your research of previous field, but with a permanent and more stable position, which is convenient for everyone. No. The first thing I wanted to tell you is that science education is not science communication. I mean, I know you know probably, but usually there's a confusion. Is know that because now there are many researchers and many physicists also that are doing science communication, very good science communication, but this is not my case. I mean, I am not a science communicator. I am in the science education department, and we do different things like all of this. The science education department at universities do research about these things. For example, how do students learn science? This is a kind of a diagnosis of how do they learn sciences, okay? For example, mental models or learning experiences. How do they react to different learning experiences? If they are more experimental, if they are more memorizing things, if they are more practical, if they are whatever, okay? They research about that. Then, under the point of view of teachers, they also analyze how teachers should teach some concepts. This would be the treatment of the diagnosis that I told you before. For example, in the learning experiences, either particular methodologies or teaching sequences, you can analyze a particular methodology. I mean, if you have a particular teaching methodology and you want to analyze it, or if you have a teaching sequence that is about a particular topic, but using different methodologies, you can also research that. You analyze the role of argumentation, inquiry-based science, the use of materials, etc. Okay. You in this field, there are researchers that also do research about how to evaluate or how do children and teenagers think of science or science perceptions. Is a very broad field, as I told you, and it's like how in general science are taught and how should be taught and how to teach and how you implement all these things. I am going to tell you the 4 topics that I am now working on. The first one is the teaching of inquiry in primary schools. That it means how to teach children to learn science process skills. This is not so much about teaching science concepts, although it's related, of course, because you cannot learn science processes about nothing. I mean, you have to learn something at the end. But we are focused on studying how to teach children to do observations, how to teach children how to make questions, how to teach children how to build hypotheses, which is very complex for very young children. We are also training them to make a fair experiment, to differentiate between an experiment that is not fair from another that is fair, that is well built, and also to come up with conclusions and some communication skills. So all these science process skills that involve science in general, and that is very different to teach depending on the course in primary school, because it's not the same 6-year-old child than a 12-year-old child. No? So you have to take into account many things. What do they need for each stage? And it's quite exciting. I mean, I like a lot this field of study, but it's also very, very complex, right? So in this way, we analyze teacher knowledge of science process skills or science in general, and it's quite surprising that many teachers in primary school actually do not know the science process skills. They do not know how to build a hypothesis, or what is a fair test or an unfair test, or so we need to do training for teachers in this sense, because they first need to know it, and then they need to know how to teach children to know it, which is different also, right? Then we also did the analysis of how future teachers are taught at the universities in this sense. This is very important because at the universities in science education, there are many initiatives related to we need to do more experimental science in primary schools. We need to do more lab, more not so theoretical, blah, blah, blah. But then you need to teach these future teachers how to introduce these science process skills, because it's not easy. So we analyze in the universities how they are doing. We also create proposals, particular proposals of teaching science sequences where science process skills are taught. So we go to the schools, do it with children, and analyze and investigate the success or not success of these proposals and so on. Then we also study, another topic is previous ideas or misconceptions in science. This is I think it's very popular that science is one of the fields that has more misconceptions related to it. And in particular, they start to build when children are very young. And it is normal, because science in many times is not intuitive. You know that it not always responds to the common sense. Most of the times is not about common sense, and you need to do the scientific process to get the right answer, right, to a question. But it's very interesting to understand how these misconceptions or these previous ideas are built in their minds, because that gives you the right tools first to diagnose what is happening, and then to overcome. This is an example of a previous idea that is built in children. These are the models of Earth and how gravity acts on objects. And this is the first model that children have in their minds. You have a plane, you don't have a sphere, you have a plane, and there is an absolute down and there's an absolute top and bottom, okay? And things just fall down. Then they learn this sphere model, but as you can see, it's like a plane, because they imagine themselves inside the sphere. I mean, not in the surface, and things go from the top to the bottom. I mean, it's not the right model yet. Then you have these two models at the same time. This model is a sphere. I mean, they know that we are in a sphere and we live in the surface. But if you are in the South Hemisphere, sorry for the Latin American people, some of you, if you open a bottle, then the wine goes to the universe. I mean, you do not keep the liquid inside. And this is a very interesting model because for some children, you have that the Earth is just like a plane. I mean, it's not a sphere, but the rest of the universe is like a sphere. So they differentiate the Earth like the things that happen here are from top to the bottom and so on. This is a plane. They differentiate that from the rest of the universe, and this is like very pre-Newtonian physics, if you remember, no, from science history. This is a view that is very, very, very pre-Newtonian. Well, and this is the right model. This is just to give you an example of these things that are very, very studied from the 90s. There are many studies about children's previous ideas and misconceptions, and also teenagers, but we already have them, and there is a lot of research around that. These are cartoon examples of how we confront with children different ideas that can explain a particular phenomenon, and they have to write their opinion, and then they have to say what the different explanations, how they are related, or what factors are not okay. And under a teaching point of view, the future teacher, what has to identify in each of the misconceptions is what is the mistake, the kind of mistake that the children is doing. And this is very important because the kinds of mistakes are also, I mean, they are known. I mean, you can categorize them in a table that is not very, very large. I mean, there are 6 or 7 kinds of mistakes. You can group all of them, and they respond to different mind mechanisms. Okay. So in this sense, I want to cite recent research that we are doing with Anabel Morales, that I don't know if she's here maybe, but she is from our field, and we analyze the misconceptions related to radioactivity and also the social impressions, right, about radioactivity. Another topic that I'm working in science education is related to modeling and embodiment in science teaching. Doing models in science teaching, or knowing how children model the reality is very important to diagnose, and this is related to the topic I told you before, and also use them to teach, use them to learn science. Actually, modeling, I mean, we all do models to build science. So how to use them in science education in primary and secondary school. And in particular, I'm doing, we are analyzing a particular way of modeling, which is called embodiment. And it consists in doing these models, doing these representations with the bodies. I mean, using the body to build a model, a particular model, of course, under a very qualitative point of view, to analyze the variables that are involved and not involved, and to learn a phenomenon, right? So you always have this scheme. First, you have an initial observation or a description of the real phenomenon. Then the students have to identify the variables that are involved, and then the variables that are going to represent. And this step is very important, because to decide which variables you are going to use to build your model, you have to make a very important decision, and you need to know what do you want to represent. And this is related to the cow that I was showing you before, the famous cow, no? I mean, it's which is the best model, this one, the first one, or this one? Well, both or none, depending on what you want to study, right? If you want to study the cow's distribution in a huge field, maybe this is okay. But if you want to study, I don't know, the water distribution inside a cow, maybe you have to go to this. So this, in the learning process of a child or of a teenager, is not easy. And it is very useful they think about it. They have to think about which variables they are going to use to build a model. And for that, they have to analyze the analogies and differences that their model has with reality, and also the limitations. The model has to have limitations. This is for sure, because the model is necessarily simpler than the reality. Otherwise, it's useless, okay? And then they iterate the process until they have the good model. This is very useful modeling for studying macro and micro phenomena, okay? Phenomena that is far from the human eye in general. This is an example of modeling with embodiment, okay? Here, some students are trying to represent the how planets orbit surrounding the sun in order to explain this impression that we have from the Earth that some planets move forwards and backwards. Okay, this is a very known phenomena. And they have to explain that with the heliocentric model, and they have to see it, right? And this is a representation of the liquid state, the molecules inside a liquid state, and well, they have to build, well, in principle, you can think that these are very simple exercises, but under a teaching point of view and the research that we do in science education is quite important. The different variables that are involved in the students when they do these models. The embodiment has a very important advantage, and is that it allows to represent phenomena that are dynamic, that is not static, okay, because they can move. And since they are the agents of the model, they can think more thoughtfully of the model itself. We also do models in particle physics education in secondary school. For example, it's very interesting when you ask them to represent why protons do not repel each other in the nucleus. The answer to this question is because of the strong force, okay? But when they still don't have the quarks ingredients, where they only have the protons and neutrons ingredients, this classical model, they try to explain how protons can be together in the nucleus and start to do very interesting hypotheses with the neutrons, like neutrons neutralize the protons, neutrons are in between two protons, or neutrons surround the protons so they cannot escape. So you have to analyze all these hypotheses with them and confront them. And then when you give them more ingredients, they are able to build the real model. And my last topic is particle physics teaching in secondary school. This is related to my previous education in my previous job, no, as a PhD in particle physics. And we analyzed modeling, embodiment, and teaching sequences, and how in general teach particle physics in high school. Actually, there are many concepts related to particle physics in high school. What is matter made of? How do particles interact? The fields, classical fields, but also quantum fields. And it's very important that in science education research, we propose new ways to introduce some concepts and so on, or at least we study what is the best way to do it. So these are the results of one of our studies. I don't think it's very interesting to go into detail, but just for you to have a very short view of that. The green color means that they have a good knowledge about the topic, about particle physics in general. The orange is like 50-50. Sorry, the yellow is 50-50, sorry, and The orange is that they have a low knowledge, okay? You don't know the questions that we made them, but just for you to have a very short view, the first 3 blocks of questions were about concepts, either classical concepts of particle physics or more modern concepts of particle physics. And as you can see, they have, in general, a low view, no? A low knowledge of particle physics. And the 4th block is about things related to, they would like to learn what is the CERN, what is the LHC, what is like things that are more related to media, more motivationally things and so on, if they would like to learn about that. And this is more green. So they have like a good impression of the field, but their knowledge is very low in general in high school. Well, this is one of the studies we do, just to have a diagnosis of what is the level of knowledge about a particular topic, and analyzing the different answers, we can build a teaching sequences and test it. Actually, our teaching sequences try to teach all these things in high school that maybe you can think is too much, but under a qualitative point of view, it is possible to teach all these things. And it is not that it is not only that it's possible, that we think it's better, because some concepts are better understood, okay, than if they don't know some things related to that, okay. And well, I am finishing already, and the final point is politics. This is going to be very short. I think actually politics and particle physics have nothing to do with each other. But the presence of the values of science in politics, I think, is necessary. The way of thinking, the way of making decisions, etc. I don't know if I represent that well or badly, but I try. Actually, well, this opportunity of being part of the Valencian government came because I have my political group that I stay with them apart from my career, and then they come up in the government and they just picked me as one of the persons that could help them. And I am trying to work hard with them for science related things, more related to climate change and environmental politics. And when I was preparing my candidature as a candidate, I had the opportunity to do a presentation with my friends called Escépticos en el PAF. And we were talking about a very important thing, that is the anti-progress tentative of some groups sometimes. Although my group is left, but we know that there is a tentative that is very anti-progress, is very anti-science, and we need to fight with that. I mean, we need to introduce the values of science inside also the decision making and the politics. I think things are going better, but in general, the science alphabetization, right? I mean, the science knowledge in general, we need to make it broader. We need to make it deeper, and it is very important. And I am trying to put my I don't know, whatever I can in that. And finally, I like to say that physics and politics are alike to the extent that they both represent the functional application of theory to make the real world work. And yeah, this is all. Thank you for your attention.
Okay, thank you very much, Paula. It's been a very interesting talk. Makes me a bit envious that I only do particle physics, being, so many interesting things to do out there. So I don't know if there are questions from the guests.
Hi,
right now.
I do have a question.
Yeah, go ahead.
Thank you for this nice talk. I was just wondering, how would you describe the learning curve to go from particle physics to start doing research related, like educational research? Like in terms of the skills that we learn in the other sciences. Could you please talk about that learning curve for you at least?
Yeah, I needed to do a master because
Okay.
yes. I mean, it's not direct. Of course, since it's a multidisciplinary field, they looked for a physicist, so it's okay. But I had to do a master on science education. Yeah, you need to know. I mean, it's a field itself, and they have their particular tools. And yeah, I mean, things related of the basis of science education, that is like theoretical, and they also use a lot of statistics. I mean, this is not very difficult, but these are different statistics than the one that we are used to, or at least the one I used to. Okay, so yeah, but I did a 2-year master.
Yeah. Yeah, that was what I was asking, because some people like do their PhDs in educational research
sure.
physics. So yeah, okay, thank you.
Great. Before we go to the next question from our guests, we have a question from YouTube. So let me read it. It's from Saira X1. So she says, "Hi, I have 2 questions just by curiosity. First, you said that you switched from particle physics at the beginning because you wanted to work in things more related to daily life. And why was that? What motivated you to look for things related to daily life?"
I don't know. This is very philosophical, I think. Well, I don't know. This is related to everyone's, no? What do you like or what you don't like? At the end, and I hope no many people is listening this. I was getting a little bit bored of calculating radiative loops related to Higgs, and I was like, okay, what I am doing with my life? I mean, is this what I want to do with my life? And I decided that I wanted to switch. But I think it's related to everyone's. I mean, I am very, very proud of have learned all that. But I am very sure that I don't want to work on that. So for me, it was easy, and I tried to another field that it was more related to the daily life. I don't know.
I guess it is somewhat also connected to the point we're at in particle physics, right? Where it's so easy in a way to come up with models, and it's such hard work. And at the end of the day, you really don't have that much info. I mean, you have a lot of info coming from experiments, but they're like, no, it's not that. No, not that either, right? So maybe that's a little bit frustrating and would make you, want to go elsewhere. I don't know if the other guests have opinions regarding this also. Well, Paola Ferrari is actually listening to this, and she says that Feynman diagrams are boring. Well, all right. So,
I have
yeah,
a question.
go ahead, Roberto.
Maybe Nicolas has questions also. He wrote something in the chat.
No, there's just a question from the chat.
Okay, let me make a question to Paula. That was, I mean, it was very interesting, especially because most of us, or also maybe part of the audience, also some of them that maybe they are teaching at the schools or in universities. So all the some of the methods that you were presenting to the embodiment of to teach concepts are kind of is a nice input to know that maybe to teach, I don't know, classical mechanics, maybe it's better just to take a student and, okay, move, run, jump, or whatever. So the question is how this method or how this trend to try to teach better science helps, for instance, to fight with the anti-vax movement or 5G people that are scared of the technology, scared, like you were saying that, because at some point you said in politics, there are people from all the sides that are against science, and let's say, maybe because at the school they thought that was too complicated to learn, or why to learn, that everything is invented, so I don't need to know how to work the cell phone, I just need to use the cell phone, for instance. I don't know if you can comment on that.
Yeah, sure. I mean, one of the topics that some researchers in science education do is this one that you are mentioning. I mean, how science education can help to have a higher science education, but for all the society. I mean, not only for the specialists in science, no, or for people that has a job related with science, but for all the society. And yeah, I think a better science education for sure contributes to have a more educated society in general, or at least a society that don't hate sciences. I mean, because this is also very important. Okay, I decide to do another thing, but well, at some point I can read about it, or I can understand, or at least I understand what is the scientific method. And I am doing this, but you know. So yeah, for sure, science education, and this is one of our most important goals in the science education research field, because I think it's quite general and it's quite shared in all countries that sciences sometimes are not the first chosen. No, I mean, we have this problem in high schools, and yeah, I don't know if I answered.
No, yeah. But one, I mean, another question, also a little bit with the comment that Paola wrote about the Feynman diagram. I guess, I don't know. I'm just wondering about. I guess Feynman diagram, in some sense, for the people that study particle physics, is kind of the first approach of the embodiment, because it's much easier to understand a process if you can draw it, kind of like pictures of the process, than with the mathematics that is behind, even though both are one-to-one and you can understand from the diagram the process. I don't know if it is possible, or people have tried to teach not the mathematics behind particle physics, but how to draw the diagram, the process with the, maybe like
Yeah,
kids, it's very easy to start to
yeah,
imagine.
yeah, for sure. Modeling in science education is a topic, is a particular topic, and you can use different tools. One of the tools is embodiment, okay? That is the one I mentioned, but there are many others. You can also use drawings, for example, or you can also use formulas. Formulas are also models at the end. And yeah, and you can start with a simple drawing. I apologize from my English. Sorry, because 3 years ago, I taught in English all day, but the practice is very important when you use another language. Okay, sorry. Yes, you can use drawings also, and you can complicate them until you have the better version or the best version, sorry, of your model you want. Mm-hmm. And these tools are used actually by many teachers in secondary school. The difference is that they are not investigated under a science education research, but they are spontaneously used by many teachers. Many teachers do embodiment, many teachers do drawings, but in science education is not a field like physics. I mean, it's quite recent as a research field. So there are things that need to be systematized. There are things that need to be analyzed, and so on.
Great. We have quite a lot of questions on YouTube. So comments. So let's go to another one. So this one is from Danilo Machado. And he says, what is the most bizarre thing that you can apply particle physics to? That you have applied particle?
Can you repeat, please? Sorry.
Which is the strangest thing, like the least connected thing that like you've been doing something like, oh, well, I can use particle physics to address this.
I don't know. I don't know.
You've never used a Feynman diagram to convince an opposite politician that you're.
I will try. I don't know. I think in programming is very useful in general, and you can apply it to many fields. And high-level mathematics, I mean, maybe you don't use this kind of maths in other fields, but they are there somewhere helping you to do many things. For example, I read that there are a study that people that has this high level training in mathematics and programming and so on, then they read like more these bureaucratic readings related to justice and so on. That is also a complicated language related to courts and so on. And they can do this comprehension, this understanding better than others and so on. This is just to, but I think it's useful in general. I don't know.
Before we continue with the questions from YouTube, maybe a guest here has got, some of the organizers have got any questions to Paula? Okay, so I'll keep on with the YouTube. So there's a PhD student doing theoretical particle physics and is thinking of switching to another field due to work stability mainly. So the question is if you can give advice on this.
Mm-hmm. I think complex systems is a very innovative field that touches different fields itself and is quite, I don't know, is related to many researches that are important and useful today. And yeah, I mean, it depends on the institute, it depends on the group, as always, but the kind of research that you can find in these fields that are like multidisciplinary and also that are connected with applied science and so on are in general very active, and they receive money and they have money for projects and so on. But I don't know. It's important that you like the field and you like what you are doing, because in any case it's hard work.
Great. We have a question from the audience here. Mauro has got a question. I don't hear you. Does everybody hear? Does anybody else hear Mauro?
Yes. Can you hear me?
Yes. Go ahead.
Yes. Good. Well, first of all, thank you very much, Paula, for your nice talk. I think it's very important to give examples and also to encourage and motivate people to think outside of a box and look for other opportunities also. And so I think that's very valuable. My question is related to science education. Once I heard a comment, and I think it's true, that it said that scientists are very scientists for whatever they do, except when it comes to teaching, because they are not very scientific, and nobody wants someone to come and tell you, so you have to teach this way, you have to improve this, and you have to improve that, read the literature. Like, it seems that we underestimate the important work that it's been done in science education. I think there is a bit of truth in there. But on the other hand, I can also somehow understand a bit of reluctance there is regarding the findings of science education, because you see, when you do a study, and this is what I would like you to explain us, is when you do a study, you do it with a group of people. Mostly, in most of the cases, it's based on, for example, one city in one university or one groups of high schools, whatever. But it turns out that it's very dependent that city where you pick some schools, and so I'm not so clear as to how faithful is to transport that reality, that cultural context from one city or from one group, say I don't know, 15 years old in high school education in some country in Europe may be very different to some other reality in Latin America, Asia, or the United States. So I would like you to tell us a little bit about this. How faithful is this to transport whatever your findings are from one reality to the other? I don't know if
Yeah,
the
very
question makes
interesting.
sense.
See, yes, a lot of sense. Social sciences are very context dependent, always. Social sciences in general, not only science education, but in general social sciences. But all humans have the same mind structure. And for example, the previous ideas that I told you before, the misconceptions related to science are the same in all countries, in all teaching systems, at the same ages. So, I mean, you can find patterns, you can find things that repeat among different countries, among different contexts. But of course, one of the most common studies and easiest studies that you do in social sciences is to replicate a study that has been done in United States to here, just to check that is the same. you understand? This is this is a practice that is very common in social sciences, doing replications and try to differentiate the social variables. But yes, of course, there is always a very strong they are very connected to the social context. So of course you have to take these variables and take them into account, but you can build also experiments to isolate them, right? And I agree with the first comment that you did about scientists in general. How do they teach? I think it's in general because we used to give to the concepts the strongest importance. No, I mean, this is very important. What I have to say, not how do I say it, what I have to say. And I agree. I mean, the conceptual. I mean, the conceptual chart of a field or whatever topic that you are going to teach is important. And if you go to university, more important than in the high school and so on. So the chart is larger. But yeah, you can study also how to do it better. And you have a field, but it's a recent field. So the field also needs self-confidence to show the importance of the field. So,
Okay, thank you very much.
Great. We are almost in the hour. I don't know if there's any final questions for Paula. Let me check. I think that on the YouTube everybody was just saying thank you. Yeah, that's it. There's one question. I remember we had a conversation a long time ago when you switched to complex systems, that you were saying that it was so strange compared to particle physics, because in particle physics you basically have all the rules set out, right? Yeah, like you have your Lagrangian, and then once you have the Lagrangian, blah, 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 okay, everything is more or less straightforward, right? And in complex system it was kind of like another world, because you didn't have all of these set rules. You had to make them up on the way. So it seems to me that now you have left these strict rules behind and are now more into building things from the bottom up. So how do you feel as a particle physicist doing this kind of thing now? Do you enjoy it more than our stricter approach?
yeah, I miss it. Yeah, because, well, part of my impression at that time, it was maybe because I didn't have all the knowledge that you need to have. I mean, you understand what I mean? I mean, when you start in a new field, you are like doing things, blah, blah, but you have statistical physics, and from there you can derive many things that can, I mean, take into account of whatever happens in complex systems from these some general prescriptions, but it's not the same as in fundamental physics. But I don't think if there's, is there anything like fundamental physics in this way? I don't think so, because we are like to the very close to the very basis things, no? Like from there you have everything, and then you go to the real life, and if you want to find the connection, there is, of course, but if you want to find it, is very, very tough. It's very complicated, and it's not worth many times, because you are not working in the connection. You are working there in another world, completely disconnected. There's a connection, and this is the same in all fields. I mean, you want to find this derivation, and I feel very comfortable there when I find this connection, but it's not worth, no, in some other fields, more in politics or yeah.
Great. So I don't know if there's any last urgent question. There's nothing else on YouTube, I think. Yeah. So I think it's a good time to wrap it up. So thank you so much, Paula, for this very interesting colloquium. It's been great having you around. And before we log out, let me remind our viewers that next week we have another webinar, this time by Oro Coutois, or however you pronounce her name. I've never been able to pronounce her name correctly. Talking about basically mesons and hadrons and baryons and all of those things that she always does. So stick around. Okay, so everybody, we'll see you next time. And thanks again, Paula.
Thank you, everybody.